Hello everyone, Cyberzilla here, and in our first video series we're gonna debug an easy C program with GDB. We are going to examine our binary with some simple GDB commands and analyze them one by one. So let's get right into it. I have written this simple C program. It's fairly obvious what we will do. It's a simple piece of C code that will print hello world 10 times. But let's compile it just to be sure. We will use GCC, that is a free C compiler that translates C into machine language that a processor can understand. The output translation is an executable binary file which is called a.out. So if we use GCC first prog, we can find that we have the binary a.out, and if we execute a.out, it prints hello world 10 times. The binaries out instructions are written in machine language, an elementary language the CPU can understand. Compilers are designed to translate the language of a C code into machine language for a variety of processor architectures. As long as the compiled program works, the average programmer is only concerned with the source code, but a hacker realizes that the compiled program is what actually gets executed out in the real world. With a better understanding of how the CPU operates, a hacker can manipulate the programs that run onto it. We have seen the source code for our first program and compiled it into an executable binary for our architecture. But what does this executable binary look like? We will use the GNU development tool debugger called GDB. Debuggers are used by programmers to step through compiled programs, examine program memory, and view processor registers. A programmer who has never used a debugger to look at the inner workings of a program is like a 17th-century doctor who has never used a microscope. A debugger can view the execution from all angles, pause it, and change anything along the way. So, if we use GDB a.out, we are now inside GDB, and if we break the main and run. The processors also have their own set of special variables called registers. Most of the instructions use these registers to read or write data. So understanding the registers of a processor is essential to understanding the instructions. So if we use info registers, we can see the registers of our binary. So the first four registers are known as general purpose registers. These are called the accumulator, base, counter, and data registers respectively. They are used for a variety of purposes, but they are mainly act as a temporary variables for the CPU when it's executing machine instructions. The second four registers are also general purpose registers, but they are sometimes known as pointers and indexes. These stand for stack pointer, base pointer, source index, and destination index. These registers are fairly important to program execution and memory management. We also have the RIP, which stands for the instruction pointer register, which points to the current instruction the processor is reading. Like a child pointing his finger at each word as he reads, the processor reads its instruction using the RIP register as its finger. So let's quit our program and then remove the a.out, and let's use GCC with the flag g first prog.c. The G flag can be used by the GCC compiler to include extra debugging information, which will give GDB access to the source code. So if we use GDB and use the Q flag, which is about quiet mode, and we execute the a.out, now we can use list, and we have access to the source code. Now if we disassemble main, and as you can see, the syntax here is not so much readable, so what we can do is set disassembly flavor to Intel, and if you disassemble main, now it's much more readable, and I prefer this syntax, so I'm gonna be using it. So first we have the source code listed, and the disassembly of the main function is displayed. Then we set a breakpoint at main, and we run the program. This breakpoint simply tells the debugger to pause the execution of the program when it gets to that point. Since the breakpoint has been set at the start of the main function, the program hits the breakpoint and pauses before actually executing any instructions in main. Now, if we use info register RIP, we can see where the instruction pointer is currently pointing at. And we can see it's the address 13D, and it's right here. So if we disassemble main, we can see the arrow here is pointing to this address. It's where the instruction pointer is. These instructions before are collectively known as the function prolog and are generated by the compiler to set up memory for the rest of the main function's local variables. Part of the reason variables need to be declared in C is to aid the constructions of this section of code. The debugger knows this part of the code is automatically generated and is smart enough to skip it over. Now, since a running program is mostly just a processor and segments of memory, examining memory is the first way to look at what's really going on. The GDB debugger provides a direct method to examine memory using the command X. We can use the examine command in GDB to look at certain address of memory in a variety of ways. This command expects two arguments when it's used: the location in memory to examine and how to display that memory. So if we wanna examine the instruction pointer register, we can use the X command examine, and we wanna what mode we wanna display it. So octal mode is O RIP. If we wanna examine it in hexadecimal, we can use XX, and again the register we wanna examine. A number also can be prepended to the format of the examine command to examine multiple units of the target address. So we can use this, and we have two instructions. If we want, let's say 12 instructions, we use this command, and we have 12 units at the target address. The examine command also accepts the format letter I, short for instructions, to display the memory as disassemble assembly language instructions. So if we use XI and RIP, we can see the whole instruction of where the instruction pointer register is pointing. But what does this do? This assembly instruction will move the value of 0 into memory allocated at the address stored in the RBP register -4. This is where the C variable I is stored in memory. I was declared as an integer that uses 4 bytes of memory on our processor. Basically, this command will zero out the variable I for the loop. So if we use info register RBP, we can see the address of the RBP where it's pointing to. But I want to examine the RBP -4. So if we use 4CB and we take the RBP -4, we can see that it's all zero out. If we use it in hexadecimal, so as predicted, it zeroes out the 4 bytes found at RBP -4, which is memory set aside for the C variable I. Then the RIP advances to the next instructions. The next few instructions actually makes much more sense to talk about in a group. So we use next I to go to the next instruction, and then if we view X10I RIP, we can see our 10 next instructions. So The first instruction is a jump. This tells the RIP to jump at this address, which is right here. So if I use next.i and I disassemble the main, we can see that RIP went where it said it would go. So what does this do? This compares the value that is in the RIP -4, which we saw it was 0, with 9. And then it goes here to jump less or equal. So if 0 is less or equal than 9, go to this address right here, which is here. So if we use next.i and we disassemble main again, it goes to jump less or equal, and we know that 0 is less than 9, so we will go to this address right here. So if we use next.i and we disassemble the main, it's exactly where it's supposed to be. So these three instructions combine to create an if-then-else control structure. If the I is less or equal to 0, then go to instruction at this address. So the next instructions, these two instructions right here, are, so this instruction is actually called the puts function. It puts the data string, these instructions. So we have these two instructions. This is setting up for the function call, and this is actually the puts function. It prints the data string. But let's examine this address to see what is written here. So if we take this address and we examine it in 4 unsigned bytes, we can see these 4 integers, and trained eye might notice something about the memory here, in particular the range of the bytes. After examining memory for long enough, these types of visual patterns become more apparent. These bytes fall within the printable ASCII range. Thankfully, GDB's examine command also contains provisions for looking at this type of memory. So if we use the C format letter, we can automatically look up a byte on the ASCII table. So X4 SB, and we can see that this is printable in H character. 101 is the E character, and this goes on. And if we use the X in S, this address is the hello world. So this has the hello world, and this puts the data string into our screen. These two instructions basically just increment the variable I by 1 and compares the variable I with 9 again, and it does the same things until it finishes the whole process. So that was for our first video. We will talk more about registers, and we will debug more complicated programs in the future. If you have any questions, I would be glad to answer them all. Thank you for watching, and I hope you have a beautiful day.